This course is all about optimization, how to build optimization models, and how to find solutions to those models using state-of-the-art solver products. In this video, we'll discuss how solvers can help organizations make better decisions. Let's start by considering a real-world example of an organization that faced an extremely complex decision. The School District of Philadelphia was faced with the problem of allocating bus routes across a number of competing bus vendors. If you think of an individual school that serves a number of students that are geographically dispersed, for that school, a set of bus routes must be determined that picks up each of these students each morning and returns them to their homes in the afternoons. Even for a single school, the allocation of these bus routes across vendors can be a complex problem. For the School District of Philadelphia, which consists of over 300 schools serving over 39,000 students, this became an extremely difficult problem. In fact, in order to serve all of these students, 725 different daily bus routes were required, and the school district had received bids from 16 different vendors, each wanting to serve a subset of the available routes. Clearly, the school district was faced with a very complex decision. As it allocated these routes, it wanted to keep in mind a number of important considerations. First, it did not want to allocate more than 300 routes to any single vendor because that would expose the district to too much risk in case of a vendor bankruptcy. Other considerations that needed to be taken into account were the experience of the different vendors, their past performance, and their financial stability. In addition, each vendor might specify a maximum number of routes that they would accept or a minimum number of routes that they would accept before agreeing to any contract. Overall, the complexity of the problem became so high that the school district was faced with a truly daunting set of decisions. For this particular problem, the School District of Philadelphia used the exact tools that you will be learning in this course, Frontline Systems Solver products, to find the optimal allocation of the 725 bus routes across the 16 vendors. In the end, 12 of the vendors were selected to serve bus routes, with the number of routes allocated to each vendor ranging from 4 up to 97 routes. Clearly, it would have been impossible for the school district to find this solution without the aid of an optimization model. For problems of this complexity, brainstorming and trial and error approaches are clearly insufficient. And this is the critical fact that makes the skills in this course so important. Complex decisions, such as allocating those 725 bus routes across the vendors, require a structured approach. It's simply not possible for organizations to tackle such important and complicated decisions using a trial and error or intuition-based approach exclusively. For these decisions, business leaders need to have confidence that they have identified the best course of action, given all of their options and all of the constraints within which they must make their decisions. This is exactly what optimization modeling enables you to do. Approach extremely complex decision-making in a structured fashion that guarantees that you've identified the optimal set of interrelated decisions. So clearly, optimization modeling is a powerful tool if it can identify the optimal solution of a problem as complex as the one faced by the School District of Philadelphia. But what is optimization modeling? Well, at a very basic level, optimization modeling involves allocating resources across a number of potential uses. That is, as a decision maker, I have a number of resources at my disposal and a number of uses to which I could put those resources. How I best allocate my resources across those uses in order to optimize my objective is the essence of optimization modeling. In the business world, these allocation decisions are often very complex and often involve many interrelated decisions that need to be made while keeping in mind a number of constraints. Let's look at a couple specific examples. Take, for example, an investment manager. In this case, the resources available can be thought of as the dollars available to invest. The uses to which those dollars can be put are the different investments that are available. I've listed 4 here, but of course the universe of total possible investments involves a huge number of different stocks, mutual funds, etc. As the investment manager, I would need to allocate my resources across these uses. Clearly, there is a nearly unlimited number of different ways that I could make those allocations. If my goal is to maximize my expected return from my investments, I also will probably need to take into account a number of constraints. For example, perhaps an upper bound on the amount of risk that I'm willing to tolerate, or bounds on different types of investments such as small cap, large cap, etc. Choosing the very best allocation of my dollars across all of the potential uses is clearly a very complex problem, but this is exactly the type of problem for which optimization modeling is perfectly suited. Let's take another example outside of the world of finance. Think, for example, about a hospital administrator who needs to schedule operating rooms over a multi-week horizon. This decision maker has a number of resources at his or her disposal, for example, doctors, nurses, and the rooms themselves. In fact, each operating room represents multiple resources, since each time slot during the day can potentially be allocated for different purposes. As you can see, planning across just a few days or weeks involves the allocation of a huge number of resources. And of course, the uses to which we want to put these resources are represented by the patients in our hospital, each of whom requires an operation that might require a combination of doctors, nurses, and operating room space. Clearly, as we think about a multi-week planning horizon involving all of these different resources and uses, it's not at all clear what the optimal allocation would be. Again, if we have an ability to structure this problem as an optimization model, we will in fact be able to identify the optimal allocation of these resources. So how do I go from having a complex set of resources and uses to actually determining an optimal solution? Well, the first step is to build a model of my decision problem. I need to quantitatively represent all of the elements of my decision, starting with the decisions that I need to make. For example, in the case of the investment manager, the decisions involved allocations across a large number of potential investment opportunities. Once I've modeled my decisions, I need to model my objective. This is something that I want to maximize or minimize. In the case of the investment manager, I'll be trying to maximize my expected return from the portfolio that I create. The third element of your optimization model is the constraints. That is, as I try to maximize my expected return by allocating funds across stocks, what are the logical conditions that I need to keep in mind? And there are a number of these that the investment manager might need to consider. Once we've modeled the decisions, the objective, and the constraints, then we can let the solver do the difficult work. In fact, the solver will then find values for my decision variables that satisfy all of the constraints that I've specified while optimizing the objective. This is the power of an optimization model, and it's what we'll be learning about in the following segments of this course.